Today we are going to explore the Jacobian matrix, which is a fundamental tool in multivariable calculus used when dealing with functions that take multiple inputs and produce multiple outputs. While a standard derivative measures how a single output changes with respect to a single input, and a gradient vector measures how a single scalar output changes with respect to multiple inputs, the Jacobian matrix steps in when we have a vector valued function that maps a set of n inputs to a set of m outputs. Formally, suppose we have a function mapping from n-dimensional space to m-dimensional space, where our outputs consist of m component functions, f1, f2, all the way up to fm, each depending on input variables, x1, x2, up to xnth. Jacobian matrix is an m by n grid, where each entry in the matrix is a first-order partial derivative, specifically the entry in the ith row, and jth column is the partial derivative of the ith output function f sub I, with respect to the jth input variable x sub j. This means that every row of the Jacobian represents the gradient of one of the Jacobian output functions, and the entire matrix acts as the best linear approximation of our vector valued function near a given point. Let us look at a concrete mathematical example to see how a Jacobian matrix is constructed. Suppose we have a transformation from polar coordinates to Cartesian coordinates, which takes two inputs, r and theta, and produces two outputs, x and y. The first output function is x equals r times the cosine of theta, and the second output function is y equals r times the sin of theta. Because we have two inputs and two outputs, our Jacobian matrix will be a 2 by 2 grid. In the first row, we take the partial derivatives of x with respect to r and with respect to theta. The partial derivative of r times the cosine of theta with respect to r is simply the cosine of theta, and the partial derivative with respect to theta is negative, r times the sine of the theta. In the second row, we take the partial derivatives of y with respect to r and with respect to theta. The partial derivative of r times the sine of theta with respect to r is the sine of the theta, and the partial derivative with respect to theta is r times the cosine of the theta. Therefore, our Jacobian matrix is a 2 by 2 matrix with the first row containing the cosine of the theta and negative r times the sine of theta, and the second row containing the sine of theta and r times the cosine of theta and r times. If we compute the determinant of this Jacobian matrix, which is called the Jacobian determinant, we get the cosine of theta multiplied by r times the cosine of theta minus negative r times the sine of theta, which sine of the sine of theta simplifies to r times the cosine squared of theta plus r times the sine squared of the theta, or simply r. This result is famously used in multivariable calculus integrals to scale the area element when changing coordinates from Cartesian to polar systems. Let us consider a second example involving functions with different numbers of inputs and outputs. Suppose we have a function that takes three input variables, x, y, and z, and maps them to two output functions, f1 and f2. Let our first output function f1 be equal to x squared times y plus z cubed, and let our second output function f2 be equal to the sine of x times y times z times. Because we have two outputs and three inputs, our Jacobian matrix will be a 2 by 3 grid consisting of 2 rows and 3 columns. For the first row, we compute the partial derivatives of f1 with respect to x, y, and z. The partial derivative of f1 with respect to x is 2 times x times y. The partial derivative of f1 with respect to y is x squared. The partial derivative of f1 with respect to z is 3 times z squared. For the second row, we compute the partial derivatives of f2 with respect to x, y, and z using the chain rule. The partial derivative of the sine of x times y times z with respect to x is y times z times. The cosine times z times y times z. The partial derivative with respect to y is x times z times. The cosine of x times z times the partial derivative with respect to z is x times y times the cosine of x times y times. Thus, our complete Jacobian matrix is a 2 by 3 matrix where the first row contains 2 times x times y, x squared, and 3 times z squared. And the second row contains I times squared, and the second row contains I z times the cosine of x times y times z times the cosine of x times z times, and x times y times the cosine of x times z times. This matrix allows us to understand how tiny perturbations in our three-dimensional inputs propagate through a non-linear system to affect our two-dimensional outputs, providing an essential foundation for advanced optimization, robotics, kinematics, and machine learning architectures.